lecture, again chapter 6 only, but lecture 29. I will be doing definition of solvable Lie algebra along with some example of solvable Lie algebra and one exercise problem I will be doing in this lecture. So let me start with it. Before starting, okay, I will give you all the note first. The series L, okay, now this is from here, so there will be something L3 over here, which will be subset of L of 2, this in the bracket, then this is again the subset of this, and this is a subset of L. Now this is called derived series, which I have already told, and this is just a note, okay. Now definition of solvable Lie algebra, what it is. The Lie algebra L is said to be solvable. Now when I can say that a Lie algebra L is solvable, if for some m greater than or equal to 1 we have L raised to the power of m is equal to 0. Now let me do one examples on this. So example of solvable Lie algebras. First is the Heisenberg algebras. Now dimension of L is equal to 3 and L dash is a subset of Z of L, okay. Now this will imply what? L of 1 is equal to L dash. Now this is from the previous lecture I have mentioned. Let me go back to it. So from here it is, okay. Now this L of this one is equal to L dash. From here I have taken. Alright, so L of 1 is equal to L dash. Now this is a subset of Z of L. Now what is a Z of L? It is a center of Lie algebra. Now what is the center of Lie algebra over here? Now center of Lie algebra is nothing but if it is Z of L, right? Z of L is equal to where x belongs to L, where Lie bracket of x comma y is equal to 0 for all y belongs to, this is the definition of the center of Lie algebra, okay, this Z of L, right? And this I have already taught you all in the previous one of the chapter. Now this L of 2, let me take L of 2 now, okay. Now this is equal to what? This is L dash of L of 1 comma L of 1, this in the bracket, and this is equal to 0. Now next example is what? Now this is second one, dimension of L is equal to 2 is given. And what else? Lie bracket of x comma y is equal to x. That is b is equal to x comma y, right? So let me take like from the previous also one example I have said L of 1 is equal to L dash is spanned by one element. So this is spanned only by the one element. So let me take the L of 2. This is equal to what? Lie bracket of L of 1 comma L of n, right? L of 1 it is, sorry. This is nothing but 1, okay. Just correct this. This is 1. Okay, and this is equal to nothing but 0. Why it is 0? Because dimension of L dash is equal to 1, which implies L dash is abelian. Okay. And what is the definition of an abelian now? Have you come across abelian? Any vector spaces V has a Lie bracket, okay, defined by this x comma y is equal to 0. This is what? Abelian, right? Abelian. This will happen for all x comma y belonging to V. Now anyway, let me drop this. This is for your understanding of what is an abelian, what is a center of Lie algebra, you all should know, right? Now let me take the third example. L is equal to SL of 2 comma C. Then L is equal to L dash. Now what is L of 1? Is equal to L dash, which is equal to L. Now same thing for this thing you'll have to do. L of 2 is equal to what? L of 1, which is nothing but L comma L, which is nothing but L dash, which is equal to nothing but L. Okay, now next is what? L of 3. Now this is what? L of 2 comma L of 2. Now this is equal to what? Lie bracket of L comma L. And this is nothing but what? L dash. And this will go up to L of n. And this is nothing but L. Okay. Now I will be doing one lemma. Okay. So let me start, okay? So if L is is a Lie algebra with ideals, L is equal to I naught. So I will start from here, okay? Like this IM is a subset of this up to so on IN, then this is a subset of I, and then something will be subset of this. It is just the other way around, okay? Now this thing is equal to 0 such that ik minus 1 upon ik is abelian. Now this is abelian for all 1 less than or equal to k less than or equal to m. So here k lies between 1 and m. Then L is solvable. So let us start with the proof. We will show that L of k is a subset of ik. So what we have to show, what I am going to show is L of k is a subset of I of k for all k belongs to natural. So I will be using here mathematical induction. So by mathematical induction, for k is equal to 1, let me start with k is equal to 1. Now to show that L of 1 is a subset of I, now I have to show that this is a subset of I. Okay? And one more thing, and this is nothing but this is equal to what? L dash, right? So what I have done over here, L upon I1. Now why I have put from where this came from? Okay, so can you see this? Take L by I1 is equal to I naught. Now from, okay, now this part it was, sorry. So I naught upon I1. Now just look at here, look at this. If I put k is equal to 1, I have told you all to put k is equal to 1. So what it will be? I of 1 minus 1 upon, what it is? I 1 minus 1 upon I1 it will be. So it is nothing but I naught upon I1, right? So let me rub this part. So that's what I have done it over here. So 1 minus 1 it will be 0, I0 upon I1. Now this is an abelian. Now this implies what? L dash is a subset of I1. Now from where I have taken this? From the previous lecture, I have done one lemma. Okay, let me go to it. Here we have already proved that L dash is a subset of I, right? This. If L by I is an abelian, then this will happen. So from this I have taken that statement. Alright, so have you understood this part now? Is it clear? Now assume that L of k, this in the bracket, okay, is a subset of ik. Now I have to show that L of k plus 1 is a subset of ik plus 1. What I have to do? Now just take this part, L of k plus 1. Now this is equal to what? Lie bracket of Lk comma L of k. Now this is a subset of what? Now what is L of k? Is a subset of ik over here, right? So put in the Lie bracket ik comma ik, which is equal to what? Ik of dash, right? From that approach 1, approach 2 in the previous lecture I've already given to you all. Please do that so that you all will come to know how I got this dash, right? Now next step is what? From the given ik upon ik plus 1 is an abelian, okay? So wait, I have considered this as equation 1. You all have to consider this as equation 1, okay? Take it as 1. Then, alright, so from the given ik upon ik plus 1 is abelian, this implies what? Ik of dash is a subset of ik plus 1, and take this as 2. So from 1 and 2, what I will get is, now this L of k plus 1 is a subset of I of ik dash, right? And I have plugged it over here. Lk plus 1 is a subset of ik of dash. Now this is a subset of what? Ik plus 1. That's what I have written it here. Now this implies that L raised to the power of k plus 1 is a subset of ik plus 1. Okay, now this is directly the subset of this. Therefore L of k is a subset of ik. For all k belongs to natural. So what I have told you all is, for this part, okay, for this part you'll see, we will show that L of k is a subset of I of k, right? This. So finally we showed that L of k is a subset of I of k for all k belongs to natural. Over here, this step. For k is equal to m, then k is equal to m. Okay? If I put, wherever there is k, if I put m, what is going to happen? L raised to power of m is a subset of I of m. See, here instead of k I am placing m. And this is equal to 0, which implies that L of m is equal to 0. And this is from what? Solvable Lie algebra, right? From this definition, where it is L of m is equal to 0. I hope you all have understood today's lecture, and in the next lecture I will be proving more exercise problems, more examples. And thanks for watching, and please do this. Okay, write it down.